We're going to do a little something called de Moivre's theorem today. 6b. Now, I've heard his name pronounced a couple of different ways. I've always said de Moivre's theorem, but then I took the history of math, and my teacher said de Moivre's. So I don't know which one's right, but it looks like this. And you'll probably call it de Moivre's. De Moivre's theorem. I like to say de Moivre. I think that sounds pretty cool. I wonder if the book says a way to pronounce it. I don't know. His theorem says there's two things, okay? Letter A. We are going to do the product and the quotient of two complex numbers. Product and quotient, okay? But we're going to do it in their polar form. So, here we go. Suppose you have a complex number in its polar form. And we'll say Z1 equals R1 times cosine of theta 1 plus I sine of theta 1. Okay, so there's one complex number. It's written in its polar form already. And then let's say that we have another complex number. We'll call it Z2. And Z2 is R2 cosine of theta 2 plus I sine of theta 2. All right. So we have two complex numbers in polar form, and we want to find two things. Bless you. We want to find their product. So we want to multiply them together. And you know how to multiply complex numbers together. You just FOIL it out. And I squared equals -1. You replace that. But in polar form, it's a little bit different. What happens is you take the r's and you multiply them together. So R1 times R2. And then you take the thetas and you add them together. So cosine of theta 1 plus theta 2 plus I sine of theta 1 plus theta 2. There you go. So that's how you multiply two complex numbers in polar form. You multiply their r's, you add up their thetas. Okay? All right. Now, to do their quotient, which would be to take Z1 divided by Z2, and there's a proof for this. There's a proof in your book, actually, if you wanted to take a look at it. I don't really go through it just because we don't have time, but if you wanted to look at it, you could. It's on page 505. No, you're good? You believe me? What if I lied to you? What if that's not true? Okay. Anyways, all right, Z1 over Z2 would be R1 divided by R2. Instead of adding the thetas, what do you think we do to them? Yes! You knew it, huh? Yep. Theta 1 minus theta 2, in that order. Z1 over Z2, theta 1 minus theta 2. Sine theta 1 minus theta 2. And there it is. Okay. So let's go ahead and let's do them. Now, I know that you know how to multiply two complex numbers, right? So if I had to, you don't need to write this down, but if I had to take 2 plus 3i and multiply that by 4 minus 5i, I would never ever tell you change those to polar form first and then do it, because that'd just be a waste of time. Okay? You know how to FOIL this out. You know how to multiply. This is an algebra 2 problem. But if they're in polar form, you don't have to get them into complex form and then multiply. You can do them while they're in polar form. So this is what we're going to do. Number 1. All right. It says here that Z1 is equal to 2 times the cosine of 2 pi over 3 plus I sine of 2 pi over 3. And Z2 is 8 times the cosine of 11 pi over 6. That's 11 pi over 6 plus I sine 11 pi over 6. All right, so let's go ahead, bless you, and let's take these and let's multiply them together. So let's do letter A. We'll do Z1 times Z2. All right, I think I give you this formula. I don't think I make you memorize this. I mean, it's pretty easy to memorize. When you're multiplying, you're going to multiply the r's together, and you're going to add the thetas. But I think I give this one to you on the test. All right, so let's go ahead and let's do it. So these are complex numbers in polar form, and we want to find out what the product of them is, Z1 times Z2. We do not have to, like I said, find their complex number and FOIL it out. We can do it using polar form of complex numbers. So 2 times 8 is 16 times the cosine of. All right, now we have to add these up. We're going to add 2 pi over 3 plus 11 pi over 6. Okay? So we need a common denominator. Common denominator would be 6. So let's change 2 pi over 3 to what? 4 pi over 6? So 4 pi over 6 plus 11 pi over 6. So that gives us 15 pi over 6. Perfect. 15 pi over 6 plus I sine of 15 pi over 6. All right, now, if they ask you, wait, did I do that right? Oh, let's keep going. I'm sorry. We need to reduce. That's why. I didn't feel right. 15 pi over 6 can reduce to what? What is it? 5 pi over 2? Yes, that's much better. All right, cosine of 5 pi over 2 plus I sine of 5 pi over 2. If they ask you to leave it in polar form, then you're done, and that's it. If they want you to keep going and go into A plus BI form, then you'd have to just keep going and evaluate it, okay, like you did last night's homework. But let's just say they asked you just to leave it. There you go. All right, now let's divide them, okay? Let's do Z2 divided by Z1. Z2 divided by Z1. So to divide these, you take the r's and you divide them. So we get 8 over 2, which is 4. Now I'm going that way. I'm going Z2 divided by Z1. So it would be Z2R over Z1R. And then now we're going to subtract. We're going to subtract 11 pi over 6 minus 4 pi over 6. And what does that give us? 7 pi over 6. Plus I sine of 7 pi over 6. And that would be your answer. Okay? And like I said, if they wanted it in A plus BI form, you would just have to keep going. You'd evaluate what cosine of 7 pi over 6 is and sine of pi and distribute the 4. Keep going. Okay. All right, so let's move on to part B now. Now that wasn't de Moivre's theorem. That was just product and quotient of two complex numbers in polar form. Here comes de Moivre's theorems. De Moivre's theorems is all about powers of complex numbers. And this one's pretty cool. That last one, you know, products and quotients, that's fine and good and all, but I know how to do that already with imaginary numbers. I know how to FOIL and divide imaginary numbers. Dividing imaginary or complex numbers is tough. Remember you have to do the conjugate, top and bottom? Yeah, that's gross. Okay, but de Moivre's theorem says this. If z is equal to r cosine theta plus I sine theta. Okay? So if z is a complex number in polar form, and we wanted to find out what z to the n is, so z to the 4th, z to the 5th, z to the 10th, okay? This is what you're going to do. It's going to look like this. You're going to do r to the n, and then cosine of n times theta plus I sine of n times theta. It feels so, like, natural, right? When we multiplied, we added the thetas, because that's what we do with exponents. When we divided, we subtracted the thetas. When it's a power raised to a power, what do you do to those exponents? You multiply them. So it all kind of makes sense. But that's what the theorem says, okay? Now this is a really good theorem because it's so much easier to find, like if I wanted to, for example, find 2 plus 3i to the 17th power. Gross. Am I going to sit there and FOIL that out? No. Am I going to do Pascal triangle? No. What I'm going to do is I'm going to write it in its polar form and use its polar form to find it. Okay? So here we go. Number 2. We are going to take -1 plus I rad 3 to the 12th power. Okay? We're going to solve this. You're going to have one of these on your test because they take a little while. They take a little while. Now, it would take a lot longer if I was going to FOIL the whole thing out, which I would never waste my time. I should make you guys do that. No, I'm just kidding. I would never. Okay, so here we go. We're going to first step number 1, is you have to write this in its polar form. We need polar form. Okay? And this is what we did yesterday. So this is why I did this yesterday. This is why we're building on. Okay, so R is equal to, R is going to be the square root of -1 squared plus rad 3 squared. Good. And you get 2. You see that a lot, huh? We get 2. Okay, now I'm going to find out what theta is by going over here to -1 rad 3. And I'm going to find out what theta prime is. That's this angle in here. Okay? So the tangent of theta prime is opposite, which is rad 3, over adjacent. And do you know what that's going to give me? You should. Or if you don't, that's okay. Use your calculator. You're going to have your calculator for this whole test. 60. Yes, I heard it. Actually, I think it gives you -60, but 60 is fine because you know what to do with that. So if I do tan inverse, see, of negative rad 3, I'm in degree mode, it gives me -60. So that gives me -60 degrees. So I actually don't want that angle. I want the angle that goes to there like that. And what angle is that? 2 pi over 3? No. Yeah. Right? So this angle, this green angle right here, I want it in radians. Radians is going to be so much easier. You don't have to do it in radians, but it's just better. So this right here is pi over 3. So then that would be 2 pi over 3. So theta is 2 pi over 3. Okay, so let's write this in its trig form really quickly. So the trig form of -1 plus I rad 3 would be, R was 2, cosine of 2 pi over 3 plus I sine of 2 pi over 3. Okay, that's just step 1. That's just getting your A plus BI into polar form. Now we need to take this. Here comes step 2. We need to take this whole thing and raise it to the 12th power. Okay? So your first step is going from complex to polar. Now that we've got it in polar form, we're going to do de Moivre's theorem. So this is de Moivre's theorem. We're going to do 2 to the 12th power. Okay? Of course, you'll get your calculator for this. And then we're going to do times cosine of 2 pi over 3 times 12. Can you do that in your head? What is it? 8 pi? Yeah, 8 pi. Plus I sine of 8 pi. Bless you. All right, now 2 to the 12th is, beep, boop, 4,096. Okay? If they wanted you to leave this in its polar form, you would just leave it in polar form. But they're not going to want you to leave it in polar form. They're going to want you to keep going one more step. They want it back into A plus BI form. So here we go. We have 4,096. And do you know what the cosine of 8 pi is? Well, how many is 8 pi? 8 pi is 1, 2, 3, 4, 5, 6, 7, 8. It's right here. And that is the point 1, 0. So what's the cosine of 8 pi? Bless you. 1. And what's the sine of 8 pi? 0. And so your answer is simply 4,096. Now, if you wanted to, and I have no problem with you doing this, it's when my Algebra 2 kids know that they can do complex numbers on their calculator, because then I get kind of mad because I want them to do it by hand. If you wanted to check your answer, you could. You guys know that your calculators can turn into A plus BI mode, right? You know that by now? If you go to mode, you can be in real mode or A plus BI mode. Okay? So if I wanted to check my answer, I would do -1. Can you see that? Yeah. -1 plus I rad 3 raised to the 12th power. Okay. What it does is it gives me something weird. It gives me 4,096 minus 1.638 e negative. It does something really strange right there because it can't really it's almost 0. Exactly. This should be 0. We know it's 0. But your calculator is going to try and round it off for you, and it doesn't really work that well. But 4,096 is right there. So if you had to do a smaller one, like -1 plus I rad 3 to say the, I don't know, 4th power, it'll probably do it right for you. Nope, still doesn't. It doesn't like it. That's weird. I don't know. I'm putting it in right. Should be nice. But anyways, it turns out to be a nice answer. So checking on your calculator is not really going to help you that much. I thought it was. But. Okay.